The Standard Deviants present
The zany world of basic math.
Starring Gabrielle Smith, Galila Azret, Brad Aldous, Sean Powell, Jeremy Clavens, Ashley Fleming, Shannon Ward, Herschel Bliefeld, Malcolm Smith, Beth Kirkpatrick, and Tessa Monroe.
Oh, wow. Oh, gosh. Oh, last time I let that monkey pack my chute. Hi, I'm Galila Azres, and welcome to the zany world of basic math. Sit right down in your comfiest chair and take a load off. Over the next hour or so, we'll do our best to add to your understanding of basic math. We'll be adding, subtracting, multiplying, and dividing all types of numbers, like fractions, integers, decimals, and lots more. And you know what? We're here to help you learn, but we're also here to keep you awake with our invigorating minds and rousing dialogue.
Wake up, you lazy bum! Hey! Oh!
Now it's disclaimer time. You must remember that this video is intended to supplement a basic math course. It's not a substitute for attending class. To truly learn math, you must attend your classes, read your books, and listen to your professors. And don't forget that this is a video, so you can pause the tape, stop the tape, or rewind the tape at any time you like. And if you ever get hungry, it goes quite well with a spicy mango salsa. Don't mind if I do. Tasty. So if you need to see something one more time, just rewind the tape and watch us again. And if you don't want to see us again, then a fast-moving freeway works really well. So let's go ahead and get started with the zany world of basic math.
Part 1, Integers.
The first type of number that we'll be looking at is the integer. Integers are whole numbers and they're negatives. Whole numbers are, well, whole. It's easier to say what whole numbers are not. Whole numbers aren't messy fractions or decimals. If you take the number 1 and keep adding 1 to it, all of the numbers you get would be whole numbers. So 5, 134, and 2 million are all whole numbers. But whole numbers cannot be negative.
So, getting back to our definition of integers, we said that integers are whole numbers and they're negatives. So integers can be positive, negative, or 0.
The easiest way to visualize integers is to put them on a number line. Ooh, baby.
Ooh, integers!
A number line is a vertical or horizontal line that is marked at even intervals, or units, similar to a thermometer. These units are labeled with numbers.
Don't forget, integers are positive and negative whole numbers. And whole numbers can't be negative, a decimal, or a fraction.
Honey, is my too dry yet?
No, Ralph, it's still a little damp. 10 minutes.
Okay, here's how a number line works. Make sure all the bulbs are working and then plug it in. Alright, when you're moving to the right or up on the number line, the numbers become greater. While moving to the left or down, the numbers become smaller. So any number on the number line above or to the right of 0 is positive or greater than 0, while any number below or to the left of 0 is negative or less than 0. A number is negative if it has a minus sign in front of it.
This number line will be a useful tool when we get to operations on negative numbers. The ends of a number line go on forever because there is no end to the amount of numbers we can produce. Another way of saying this is that numbers go on to infinity, kind of like your student loans.
Integers are made up of digits.
Digits, 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 digits.
Digits are simply the numbers 0 to 9. Every digit in a number goes in a certain place.
The first number in a whole number is in the units place. The tens place is just next door, on the left. One place over from the tens place is the hundreds place.
And if you go north on Old Glebe Road and just keep going through 4 lights and a few curves, you'll be around Courthouse Road, and then you take a right on Rhodes Road and go about 5 houses. Then you'll be at my friend Igor's house. He's having a few people over this weekend. You should stop by. He's serving chips and salsa.
All right, let's go back to our number places. To the left of the hundreds place, we've got the thousands place, the 10,000s place, the 100,000s place, the millions place, the 10 millions place, and so forth. And just like we saw for the integers on a number line, these digit places go on forever. Because numbers go on to infinity.
Excuse me. Hi. I'm looking for infinity.
Oh, yeah, okay. You just need to go down to the units place, hang a left, and then keep on going.
Thanks.
Let's take a look at the number 1,492.
For this number, the 2 is in the units place. Moving to the left, the 9 is in the tens place, and the 4 is in the hundreds place. Finally, the 1 is in the thousands place. And be sure to remember this when you're trying to convince the Queen that she should give you a lot of money to sail off and find a new way to get somewhere.
Now that we know how integers are set up, we can begin to operate with them. And the first operation we'll talk about
Is addition.
Section A, addition.
Adding is putting things together, then counting them up. When you add positive integers or whole numbers, you combine them to form a larger number. When you add numbers together, you get what's called a sum.
For example, if you have 4 pieces of tripe, and you're lucky enough that someone gives you 5 more pieces of tripe,
Guess what I got? More tripe!
then you'll have 9 pieces of tripe in all.
Goody, more tripe!
The sum of 4 pieces of tripe and 5 pieces of tripe is 9 pieces of tripe.
Addition is putting things together, and then counting how much you've got. Terms such as and or plus are often used to show that an operation is addition. Both the operation of addition and the operation of subtraction can be best shown by using a number line.
A number line's a lot like an elevator. When adding a positive integer to any other integer, you will be moving up the number line, because moving up the line is an increase. For 3 plus 6, you will start at the 3rd floor on the elevator and move up 6 floors. Notice that after moving up 6 floors, you're now at 9. So 3 floors plus 6 more puts you on the 9th floor.
It's just the opposite when adding a negative number, like -4, -5,000, and so on. When adding a negative integer to any other integer, you will be moving down the number line.
That's because the further you move down the number line, your numbers will decrease, just like the floors of an elevator decrease as you go down. Addition is cool, addition is fun. I like to do addition when I'm sitting in the sun. Addition is fun, addition is nice. I like to do addition, but I don't like checking for hair lice. Addition, 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 addition. Everyone fancies addition. Addition, 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 addition. Everyone fancies addition.
So adding negative numbers is the same as subtraction. We'll talk about subtraction in a minute. Let's go back to the example we just did. This time, we'll make the 6 negative.
You still start at 3 on the number line, or the 3rd floor. Then move down 6 floors. After moving down 6 floors, you're at -3. You're in the basement. So 3 plus -6 equals -3. Likewise, to add -3 and -6, Start at -3 and move down 6 units to end up at -9. So -3 plus -6 equals -9.
Always remember that adding a negative number is the same as subtracting the positive value of that number.
Now, let's add some bigger numbers.
Adding can actually be a very fascinating process. Take, for example, this ant colony right there. Now, what I have done is I have found out which ants are male and which ants are female. To me, the most joyful part of this whole experience, to me, for me, what I enjoy doing for me, is taking the total number of female ants and male ants and bringing them together. That's the fun of the whole. You know, this is very frustrating.
So let's add the number of female and male ants that are in this colony. There are 567 male ants and 789 female ants.
To add big numbers like this, we need to stack the numbers on top of one another.
Then, we combine each of the numbers in each digit place. Start by adding the numbers in the units place. In this problem, the 7 and the 9 are in the units place. No problem. All we do is add 7 and 9 together, which gives us 16. Okay, we've hit a snag. Every digit place has room for only one digit, but 16 has two.
Remember, digits are just the numbers 0 to 9. When you add two numbers together in a digit place, and they add up to more than 9, then you have to carry over.
So the number in the tens place of any digit place sum must be carried over. Carrying over means you take the digit in the tens place of the digit place sum and carry it over to the next digit place to the left in your addition problem. You do this whenever the sum amount in a digit place is greater than 9.
After we carry that digit to the next place, we include that digit in our sum for the next digit place. Let's go back to our example.
The 7 and 9 in the units place equals 16. So we have to carry the 1 in the tens place of the number 16 to the tens place of our addition problem. We leave the 6 here, so the 6 has the units place to himself. What a hog.
Now that we've added the numbers in one digit place, we go on to the next digit place on the left, the tens place.
We add the numbers 6 and 8 in the tens place, plus the 1 we carried over. So 1 plus 6 equals 7, plus 8 equals 15. The tens place sum also has room for only one number, but 15 has two. So the 1 from the tens place in 15 must be carried over to the hundreds place in our problem. So the 5 is left in the tens place all by itself.
We'll continue from right to left for each digit place in the problem. Now we have the 1, 5, and 7 all in the hundreds place. We add 1 and 5 to equal 6, plus 7 equals 13. The 3 from 13 stays in the hundreds place, and the 1 now goes in the thousandths place. In this instance, there are no other numbers in the thousandths place, so the 1's by itself. So the result of adding 567 ants plus 789 ants equals 1,356 ants. No problemo, right?
Sí, es fácil.
So remember that when adding whole numbers or integers, you always begin with the numbers on the farthest right of the addition problem.
Oh, and when you're doing a place setting, the spoon always goes on the farthest right.
And that when you add together numbers in a digit place whose sum is larger than 9, you'll have to carry over.
Boy, and how?
Section B, subtraction.
The next subject we'll tackle with integers is subtraction.
Oh, God!
Subtraction is the inverse or reverse operation of addition. Instead of combining integers, we're taking them away.
That wasn't funny.
Yes, it was.
The answer to a subtraction problem is called the difference. Makes sense, right? The solution represents the difference between the two numbers involved in the subtraction operation.
Let's go back to our tripe example from earlier. You've got 9 pieces of tripe until that tripe-stealing neighbor of yours comes by and takes 7 pieces of your tripe. You're left with only 2 pieces of tripe. This This is the difference between what you had and what was taken away.
Subtraction is taking things away and finding out how much is left. Terms such as take away and minus are commonly used with subtraction.
As we said earlier, both the operations of addition and subtraction are best shown using the number line.
When subtracting a positive integer from any other integer, you will be moving down the number line.
For example, 3 minus 6 means that you will start at 3 on the number line, or on the 3rd floor, and move down 6 floors. Notice that after moving down 6 floors, you are now at -3. You're in the basement again. So 3 minus 6 equals -3. That's all there is to it.
Remember that we said that adding a negative number is the same as subtracting by that number. So, 3 plus -6 gives you the same answer as 3 minus 6. They both equal -3.
Now, when you subtract a negative integer from any other integer, you will be moving up the number line. That's right. Even though we're subtracting, we're moving on up.
To a deluxe apartment in the sky. Moving on up.
You see, when you subtract a negative integer, you end up with two negative signs in the equation, and a negative always equal a positive. It's the same as addition. Just think of it this way. A double negative always equals a positive. Let's do a quick example of subtracting a negative integer.
For 3 minus -6, you make it read 3 plus 6. That's because subtracting a negative number is the same as adding a positive number. This may seem a bit confusing, but it'll all make sense in a second. We'll go back to the number line.
On the number line, you start at 3 and move up 6 places. Notice that after moving up 6 places, you're at 9. So 3 minus -6 equals 9. The same answer you'd get for 3 plus 6. So remember that subtracting a negative integer is the same as adding that positive integer.
Now let's look at subtraction with bigger numbers. In subtraction, just like addition, you generally stack one number on top of the other. You always place the amount you started with on top, and the amount being taken away on the bottom.
So we'll subtract the bottom number from the top number in each digit place. And just like addition, we always start in the digit place to the far right. Sometimes you may find that you have to subtract a larger number from a smaller number in a digit place.
Like 13 minus 7. The 7 must be subtracted from the 3 in the units place. But 7 is larger than 3. When this happens, you have to borrow.
Kind of like when I borrow my neighbor's car.
Borrowing is done whenever the digit you're subtracting is bigger than the digit you're subtracting from.
In order to borrow, you must take 1 away from the digit place on top and to the left of the digit place you are subtracting, and then add 10 to the number being subtracted from.
Don't forget, if you borrow 1 from a digit place, then it's worth 10 to the digit place to its immediate right.
Think of it this way. If the digit you're subtracting from on top is less than the digit below it, then you have to move to the left to borrow 10 from that digit.
Now let's do an example where we will have to do some borrowing.
I don't know where they are. They're dead. I counted. 723 left. I don't know where the rest of them are.
Now let's do some subtracting.
We'll subtract the 287 ants that died from the 723 left. We start on the far right. The digit place in the far right is the units place.
So following the process of subtraction, we'll start with the units place. 3 minus 7. 7 is larger than 3, so the 3 has to borrow from the tens place. We take away 1 from the tens place, making it 1 now.
Hey! It's always a good idea to cross out the old number and put the new number above to make sure you don't forget that you've subtracted 1 from the original number. And remember that the 1 from the tens place is worth 10 to the units place. So we add the 10 we borrowed from the tens place to the 3 already in the units place. So now we're subtracting from 13, or 3 plus 10. 13 minus 7 equals 6, which goes in the units place of the solution.
So we've got one of the digit places done. Now we'll subtract the numbers in the next digit place on the left. We have to subtract the numbers in the tens place. Remember, we borrowed 1 from the 2, so in the tens place, we have 1 minus 8. Again, we have to borrow from the digit place to the left in order to have a positive result for the tens place in our answer. So we subtract 1 from the 7 in the hundreds place, making it 6 now. Subtracting 1 from the hundreds place is worth 10 to the tens place. There's 1 left in the tens place, so we add the 10 we borrowed to the 1 left to get 11. So the tens place is now 11 minus 8. This gives us 3 for the tens place in the solution.
The last place that needs to be subtracted is the hundreds place. Since we borrowed 1 from the 7, the digits in the hundreds place are 6 minus 2, which results in a 4 in the hundreds place of our answer. So, the answer to 723 ants minus 287 ants is 436 ants. You got your answer.
So don't forget that in subtraction, you sometimes have to borrow. When you borrow, you take 1 from the digit place to the left, which is worth 10 to the digit place doing the borrowing. Now we'll move on to a third type of operation with integers.
Section C, multiplication.
Multiplication is simply an extension of addition. In other words, if you add up 5 plus 5 plus 5, you'd get 15. Multiplication simplifies this. Instead of adding these 5s together, you'd multiply the number of 5s, 3 times 5 to equal 15.
Multiplication really comes in handy when you multiply larger numbers. Instead of adding up the number of seeds in all 63 bags of birdseed by counting each one, you could just multiply the number of bags, 63, times 421, the number of seeds in each bag.
The answer to any multiplication problem is called the product. The product of multiplying small integers, those from 12 to 0, can be found in multiplication tables. If you don't remember them, then you need to memorize them.
Or you can threaten your math professor and take him with you wherever you go. All right, Smarty. There's 2 stores over there with 4 diamonds in each. How many diamonds in all?
When you're multiplying positive and negative numbers, there are a few rules to follow. If the numbers you're multiplying are both positive, then your product will always be positive. Anytime you multiply a negative number and a positive number, you will have a negative product.
Okay, the last rule is that the product of multiplying 2 negative numbers always gives you a positive answer. These rules are the same for any types of numbers you multiply.
This law of multiplication was proved by Harry Stodomite in 1964.
Well, it was a very long process, actually. We started by gathering all the negative numbers we could find, which took several weeks. Then my team and I multiplied them all by each other to see if the products would indeed be positive. Over the next 17 months, we performed 14 trillion computations, and all of them gave positive answers.
So remember on your tests that if you multiply a positive number times a positive number, you always get a positive number. A negative number times a positive number always gives you a negative number. And a negative number times a negative number always results in a positive number.
Just like addition and subtraction, large numbers being multiplied are usually put one on top of the other, like this mayonnaise, salami, and cheese sandwich. Actors get food catered, you know?
Salami.
Arranged this way, numbers are multiplied digit by digit, just like numbers being added or subtracted.
In order to multiply 2 large numbers, like 314 times 32, you must first multiply the digit at the far right of the bottom number, in this case 2, by every digit of the top number, one by one from right to left, carrying over if necessary.
Remember that for any math problem, whether you're multiplying, adding, subtracting, or dividing, you always want to keep the digit places lined up, just like ships. I didn't keep them lined up, and Anita sank, and that was a big pain in my stern.
Let's look at a normal multiplication operation.
Ronald's attempting to become the first person to somersault across a whole state. An amazing achievement. Even if it is Rhode Island, he's been somersaulting for 23 days now. He somersaults 186 times a day. How many somersaults has he done in all?
So we'll multiply 186 times 23. Remember, you start the multiplication process by multiplying the bottom number on the far right with every digit in the top number of the problem. For this problem, the units place is on the far right.
Unless you're multiplying decimals, you will always start with the units place.
For our problem, the 3 is the bottom number in the units place. So, the first step in this problem is to multiply 3 by 6, which is 18. Remember, only one digit for each digit place. So we leave the 8 and carry the 1 to the tens place.
Whoa! Now we multiply the 3 by the next number to the left in the top of our multiplication problem. We multiply 3 times the next number on top, 8. The product of these two numbers is 24. We must also add the 1 we carried over. So 24 plus 1 is 25. The 5 stays in the tens place of the result, and we carry the 2 to the digit place to the left. We then multiply 3 times 1, which is 3, then add the carried 2 for a result of 5 in the hundreds place.
All right, we're halfway through the problem, but I know you want to see it all. So, we've got to follow the same process we just did for the number in the units place for each digit in the bottom number. We have to take one step before multiplying the next digit in the bottom number.
Notice that the 2 is in the tens place. When we multiply the 2 by the number in the units place on top, we have to put the product of those two numbers in the tens place of the result. But that means there will not be a number right here where the units place of our second result is.
You might be wondering, why are we putting the product in the tens place and not the units place?
Well, let's go back to our example and explain.
Notice that the results are placed one under the other here. The first result is the product of the bottom digit in the units place, 3, times the top number in our multiplication problem, 186. The second result is the product of the bottom digit in the tens place, 2, times the top number in our multiplication problem.
Now listen closely to this next bit of info. The units place for the product of the bottom digit times the top number should always go in the same digit place as the bottom digit you're multiplying by. Any spaces to the right of that product's units place that aren't used can be filled in with zeros. So, we put a 0 underneath the 8 in the units place of our second result. That's because the bottom digit we're multiplying by, 2, is in the tens place, and we want the units place of the product of 2 times the top number to go in the tens place as well.
So, who wants to do some more multiplying? Me!
Let's get on with this little rascal by multiplying 2 times 6, which is 12. The 2 goes in the tens place of the second result. We carry the 1 to the next column. We multiply 2 times 8, which equals 16, then add the carried 1 to equal 17. The 7 stays in the hundreds place of the second result, and the 1 is now carried over. Our last multiplication operation is to multiply 2 times 1 to equal 2, then add the carried 1 to equal 3. We put this in the thousands place of the second result.
After you've multiplied all the bottom numbers by the top numbers and put the zeros in the appropriate digit places, you can then add up all of your results.
For this example, we only have 2 results because the bottom number only has 2 digit places. If we'd had 3 digits in the bottom number, then we would have had 3 results. So the last thing we need to do is add the results. 558 plus 3,720 equals 4,278. So that's the answer, or product, to our multiplication problem.
That's how many somersaults Ronald's done in all.
Next, we'll look at exponents, an extension of multiplication.
Section D, exponents.
Exponents are a shorthand notation for the multiplication of a number times itself. In other words, instead of saying 5 times 5 times 5 equals 125, we'd say 5 raised to the third power.
The 3 is known as the exponent, and the 5 is called the base. The exponent shows how many times the base number is multiplied times itself.
Here's a couple more examples of exponents.
3 to the 4th power is 3 times 3 times 3 times 3, which equals 81. In this exponent, notice we have a negative number for our base, but that doesn't change the way we find our answer. Negative 5 to the 3rd power is negative 5 times negative 5 times negative 5, and the result is negative 125.
Now, there are a few exponents which do the same thing to every base number no matter what it is. Like, any integer raised to the 1st power is the same as that integer. So 8 to the 1st power is 8. Negative 15 to the 1st power is negative 15.
There's one other exponent that is really important for you to remember. Any non-zero integer raised to the 0 power equals 1.
So regardless of whether the number is 1500 or 2, if it's raised to the 0 power, then it equals 1.
One more thing about exponents that you can tuck away in your memory bank. Look at these numbers. Each time we add a 0, we go up 1 digit place. Now look at these exponents. Each time we increase the exponent by 1, we increase the number of digit places in the corresponding number by 1. This is just a quick note to show you how each digit place in a number increases by a power of 10. Also notice that the exponent number equals the number of zeros in each number.
Exponents are going to be helpful later on when you start dealing with extremely large numbers.
Section E, division.
Just like subtraction is the reverse of addition, division is the reverse of multiplication. We'll look at the division of integers now and deal with other forms of division later in the tape. Division is the process of breaking down numbers into equal groups.
Oh, I thought it had something to do with break dancing.
Now I'm going to give you an example of division at work. Over here, Missy. Let's say you got 27 people that you want beat up, right? Now, I'm a man who believes in sharing. So what I'm going to do is I'm going to divide up those soon-to-be black and blue peoples, right, amongst my 3 friends. So I'm dividing 27 by 3.
The number being divided, 27 in this case, is the dividend, and the number you're dividing by, or 3, is the divisor. The answer to a division problem is called the quotient. For our example, 27 divided by 3, the quotient is 9.
Now, let's reverse the process.
If we reverse the division process and multiply the answer, 9, by the divisor, 3, we'd get 27. The dividend. Pretty cool, huh?
So, division is just multiplication in reverse. You can always check your answers by multiplying the divisor by the quotient. Just like everything else, the division process becomes more involved when we're dividing larger numbers. Picture this problem.
We'll divide 581 by 34. We're going to find out how many 34s are in 581.
First, we'll put the numbers into the proper format. The dividend, 581, goes underneath the division sign. It's being divided. The divisor, 34, goes to the left of the division sign.
What we're about to show you is called long division because there's long numbers to divide. Ready to start?
Boy, and how?
The first step is to see how many times the divisor, 34, will go into the number in the largest digits place in the dividend.
The largest digit place will always be the number on the far left, since digit places increase as they go to the left.
In this instance, the number in the largest digits place is the 5 in the hundreds place. So we divide 34 into 5. We've hit a stumbling block. 34 won't go into 5. When this happens, you must include the digit to the right, so we have to include the integer in the digits place to the right, 8. So now we see how many times 34 will go into 58. 34 goes into 58 one time. If 58 could not have been divided by 34, then we would have had to include the next number to the right in the dividend. But since 34 goes into 58 one time, then the 1 goes above the 8.
Notice the 1 goes above the 8 and not the 5. That's because 34 is divided into 58, and not 5. So the first number in the quotient goes here.
The next step is to multiply 1 by 34 to get 34. You place the product of these two numbers directly below the 58. We subtract 34 from 58 to equal 24. Now we divide 34 into 24. But we first bring down the 1 in the units place of the dividend next to 24. So now we're trying to find out how many times 34 goes into 241.
The only way to find the answer to this is through trial and error. Let's try to divide 34 into 241 6 times.
To do this, we multiply 6 times 34. Then, the product is 204. We subtract 204 from 241 to equal 37. 37 is left over, but the divisor, 34, can be divided into 37 because 37 is larger than 34. So, we know we can divide 34 into 241 by a larger number than 6.
Let's try 7. 34 times 7 equals 238. 238 goes beneath 241 because we're dividing 34 into 241. If we subtract 238 from 241, we get 3. And 3 can't be divided by 34. So, we know that 34 goes into 241 7 times.
There's no more numbers to bring down from the dividend, so we're done because 34 can't go into 3. But we still have a remainder of 3 left at the end of the division problem.
A division problem has a remainder when the divisor cannot go into the dividend exactly. The remainder should always be less than the divisor. If it's not, then you know you've done something wrong.
So the answer to our division problem is 17 with a remainder of 3. It's also always a good idea to check your work to make sure some minor error hasn't thrown off the whole division process.
Remember, to check a division problem, you just multiply the quotient or answer by the divisor and add the remainder if there is one. If it equals the dividend, then you know you're right. For our problem, we multiply 17 times 34 to equal 578. Then add the remainder, 3, to equal 581. Our answer's right.
We just thrown off the whole division process.
You mean the remainder's bigger than the divisor?
Yes, General.
Sir, the president's on the phone, and he wants an answer. A correct answer.
Section F. Order of operations.
In many arithmetic problems, you'll have a long string of numbers separated by different combinations of operators. You might have to multiply, divide, and add, in addition to dealing with parentheses and exponents, all in the same problem. Here are some examples.
Don't worry, a standard order of operations has been developed just for these types of problems.
Of course, you need a standard order of operations to solve any problem. You have to do certain operations before others. Oh, why, just imagine. If I attack my opponent's marble field before his building blocks, oh, buddy, I'd be finished before dawn. Oh! Oh! Oh!
You always work from left to right with these strings of numbers. The standard order of operations is to do parentheses first, then exponents, multiplication and division are next, and addition and subtraction are last.
Lots of people use a mnemonic device to remember this order of operations. The first letter of each word in the order of operation spells PEMDAS.
Sinking in, isn't it?
Here's an example of a math problem that you must figure out using the order of operations to get the right answer.
5 squared plus 9 minus 3 times 4 minus 8 divided by 2. Now let's solve this puppy. Moving from left to right, we have to do any operations in parentheses first. 9 minus 3 is in parentheses, and it has a value of 6. So we substitute the 6 for the 9 minus 3. So the problem now looks like this.
Since there are no more parentheses left, we move on to the next step in the order of operations, exponents.
Again, moving from left to right, we find 5 to the second power.
Remember, the exponent is just the number of times you multiply the base number by.
So we multiply 5 times 5 to get 25. We put 25 where 5 to the second power is. So our problem now reads 25 plus 6 times 4 minus 8 divided by 2.
There are no more exponents. Multiplication and division are the next step in the order of operations.
Starting on the left, the first multiplication problem we find is 6 times 4, or 24. 24 replaces 6 times 4. We continue moving to the right and find a division problem. 8 divided by 2. The answer to this is 4, and 4 replaces 8 divided by 2. So the problem now reads 25 plus 24 minus 4.
Addition and subtraction operations are all that's left. Beginning on the left, we add 24 and 25 to equal 49. 49 replaces the addition operation, so all that remains is 49 minus 4, or 45. So, the answer to 5 to the second power plus 9 minus 3 times 4 minus 8 divided by 2 is 45. Okay? Everyone take a breather.
That was a good operation, huh?
Operations.
If you're going to use a calculator, then it's important to see if your calculator has a specific memory setup for the order of operations. In order to do a complex string of arithmetic on a calculator, you must either have a calculator that recognizes the order of operations or break up the string and only use the calculator to figure out specific operations within the string. In that case, you still need to use the order of operations.
Section G, rounding off.
All right, let's say you've got two big numbers to add, but you don't have time to get your paper out and do a bunch of carrying and so on. Well, then you can round these numbers off. Rounding off is a method used when you're not working with exact numbers. And whenever you round, you do it by digit place.
You can round off to the tens place, the hundreds place, and off to the thousands place, and so forth, depending on your needs.
Let's do an example. We'll round this number off to the nearest hundred.
What? I'm polishing my spear. You got a problem with that, huh?
Anytime you want to round off a positive integer, you have to take 4 steps.
Your first step is to find the digit place you're rounding off to. It's usually the last place you used it. For our number we're rounding, the digit in the hundreds place is a 4. The second step is to look one digit place to the right of where you want to round off to. If that digit is less than 5, you don't do anything yet. Don't move a muscle. Okay, you can move again. If that digit is greater than or equal to 5, then increase the digit in the digit place you're rounding to by 1.
We're trying to round off to the nearest hundreds place, so the digit place immediately to the right is the tens place. It has a 9 in it. Since 9 is greater than 5, we increase the 4 in the hundreds place, the number we're rounding off to, by 1. We make the 4 a 5.
If the number in the tens place had been less than 5, then we would have left the 4. There's one more step left.
We replace all digits to the right of the digit place we're rounding off to with zeros. We're rounding off to the nearest hundreds place, so we make all the numbers to the right of the 5 zeros. So our new number is 1,500.
If we want to round 1,492 to the nearest thousand, then the number would be 1,000. That's because the number to the right of the thousands place is a 4. It's less than 5, so we skip to the next step and replace all numbers to the right of the 1 with zeros.
You can round off any integer, no matter how large it is, if you use the steps we've just talked about.
What if I want to make up my own rules of rounding?
Section H, scientific notation.
Another method used to make calculations with large numbers easier is scientific notation. Remember we said earlier that each digit place of an integer is represented by a power of 10. 10 to the first power is 10. 10 to the second power is 100, and so on. In scientific notation, you multiply a number between 1 and 10 by one of these powers of 10. Let's do an example. We'll express the number 2,000 in scientific notation.
2,000 in scientific notation is 2 times 10 to the third power. How do we know this? Well, there's 3 zeros in 2,000. And like we said earlier, the amount of your exponent is always equal to the amount of zeros in your number. So we know the exponent's 3. 10 to the third power is 1,000, or 10 times 10 times 10. Now we just multiply 1,000 by the first digit in the number we're trying to express. In this case, the first digit is a 2. 2 times 1,000 equals 2,000. So 10 to the third power times 2 equals 2,000.
I know all of you out there want to do another. Quick! Represent 400,000.
First, we count the number of zeros to determine what power of 10 you're working with. 1, 2, 3, 4, 5. The number of zeros you have in your number is your exponent. There's 5 zeros, so 5 is your exponent.
Okay, we're halfway there. We know our power of 10 is 5, or 100,000. Now that we have the right number of digit places, all we need to do is multiply 100,000 times 4, the first digit in the number we're trying to express, to get 400,000. So 400,000 in scientific notation is 4 times 10 to the fifth power.
Remember that the amount of zeros in the number is the same as the power of 10 we're raising it by. No matter how large the number is, you can find the power of 10 it's multiplied by if you count the number of zeros. That's why this method comes in so handy for scientists studying vast distances in the galaxy.
Johnson! How are you, buddy? I think I'm going to build that deck this weekend.
Really?
Yeah.
On the back of the house?
Oh, you know it.
How big are you gonna make it?
I was thinking 2 times 10 to the first, by about 5 times 10 to the first. Big deck, big deck.
Wow. You're probably gonna need about 6 times 10 to the second nails for that one, huh? Right? Huh?
Yeah.
And one other thing to remember about scientific notation. Remember that a large number is in scientific notation when it is written as a number between 1 and 10 multiplied by a power of 10.
Oh, like 4 times 10 to the fifth power. 4's between the 1 and the 10.
Okay, we've only been looking at numbers that have their leftmost digit different from 0. After you study decimals, then you'll be able to use scientific notation for numbers with 2 digits different from 0 at the beginning of the number, like 162,000 or 29 million. So let's get to those little decimals.
Part 2. Decimals.
In the previous section, we explored integers.
Boy, did we.
We looked at the operations of addition, subtraction, multiplication, division, and the expression of large integers using scientific notation. The next type of number we'll look at is decimals. Decimal numbers are not whole numbers and can be either positive or negative.
Section A, the decimal point and decimal places.
We've said several times so far that each digit place represents multiplication by a power of 10. The same is true to the right of the decimal point. The decimal point is to the right of the unit's place. It's in every number, but it's not written with integers. That is, the number 42 could be written as 42 with the decimal point after the 2. But it's a little cumbersome to do this.
The decimal point represents the separation of the units place and the tenths place.
The place to the right of the tenths place is the hundredths place. To the right of the hundredths place is the thousandths place, and so forth.
For example, the number 52.3 is read as 52 3/10.
Addition, subtraction, multiplication, and division for numbers with decimals are a lot like addition, subtraction, multiplication, and division with integers. The important difference is that you have to keep track of the decimal places you're working with.
Decimal points are good. Decimal points are good. Decimal points are good. Decimal points are good.
Section B, addition and subtraction with decimals.
When you're adding or subtracting decimals, the decimal points for the numbers you're adding or subtracting must line up. For example, if you want to add the numbers 56.3 and 7.89, then the decimal points for each number must line up.
For this problem, we line up the 6 and the 7 because they're both in the units place of their respective numbers. Now that the numbers are lined up, we can add them just like we did with integers, carrying when needed. To help with addition, we can place a 0 to the right of the 3 without changing the value of the first number, since it is to the right of the decimal.
What do we mean by that? Well, look at these two numbers. In the first number, the zeros could be dropped without changing the value of the number. The number is still 56.3 after we dropped the zeros. For the second number, this is not possible. The second number is 56 billion.3. If we drop the zeros, it would be 56.3.
All the zeros are important in this number. All the zeros between the 6 and the 3 affect the size of the number because the zeros are to the left of the decimal.
Now that we've put in a 0, let's go back and add. Come on. Come on!
Our first step in the problem is to add the numbers to the farthest right in the hundredths place. 9 plus 0 equals 9. Moving to the left, we add 8 and 3 and get 11. We put a 1 in the tenths place of the sum and carry a 1 to the units place.
As we said earlier, it's important to keep the decimal points lined up.
So we just bring down the decimal point to right here, the exact same place, one level lower. Now we finish up by adding the rest of the numbers.
7 plus 6 is 13, plus the carried 1 equals 14. The 4 goes in the units place, and we carry the 1 to the tens place. Now we add the carried 1 plus 5 to get 6. The 6 goes in the tens place of the solution, and presto! The answer to our addition problem is 64 and 1900ths.
Subtracting with decimals is done in the same way as adding. The most important thing to remember is to line the decimal points up.
Section C, multiplication and division with decimals.
For multiplication and division of numbers, you must also keep track of the decimal places. If you don't, they'll muck up the whole thing, not to mention your carpet.
Multiplication of decimals is done exactly the same as multiplication of integers. One number is set on top of the other, and each digit of the bottom number is multiplied with all the digits in the top number, with the appropriate zeros put into each result. The results are then added together, just like with integers.
So why are you saying all this again? Isn't this just more cumbersomeness?
No, you need to take one additional step when multiplying decimals.
You have to count the total number of digit places to the right of the decimal point in all of the numbers that are being multiplied. Then, you move your product's decimal point that number of decimal places to the left from the right end of the product.
So if there are a total of 4 numbers to the right of the units place in the numbers being multiplied, then the decimal is put 4 places from the right end in the product. Let's do an example.
1.86 times 2.3 is calculated the same way as 186 times 23. After we've gone through the steps in calculating a multiplication problem, the product, or answer, is 4,278.
Now we need to adjust our product for the decimal points.
There are 3 digits to the right of the decimal points in both numbers being multiplied. So we have to insert a decimal point 3 decimal places from the right end of our product. That means the decimal point is located between the 4 and 2. The answer is 4 and 278 thousandths.
Division of decimals is also done exactly the same as division of integers, except we move the decimal points before dividing.
We'll divide 1.45 by 0.5. Oh!
1.45 goes inside the division sign, since it's the dividend, or number being divided. 0.5, or 5/10, goes to the left of the division sign.
The first step anytime you divide decimals is to move the decimal point in the divisor all the way to the right, so that the last digit of the divisor is in the units place.
The decimal point in the divisor, or 5/10, must be moved one place to the right. That way, the divisor's last number on the right is in the units place.
The second step is to move the decimal point in the dividend the same number of places to the right as we move the divisor.
So we moved the decimal point in the dividend, or 1 and 45/100ths, the same number of places to the right as we moved the divisor. We moved the decimal point in the divisor one place, so now we move the decimal in the dividend one place. Our division problem is now 14.5 divided by 5.
Now we just go through the normal division process.
Here's our division problem. The 5 can't go into 1, so we have to include the next digit in the dividend, 4. The 5 goes into 14 2 times. 2 times 5 equals 10, and it goes beneath the 14. 14 minus 10 equals 4. Now we bring down the 5. 45 divided by 5 is 9 with no remainder. So after dividing 5 into 14.5, our quotient is 29.
Our last step is to insert a decimal point into the answer, above the decimal point in the dividend.
The decimal place directly above the decimal point in 14.5 is between the 2 and the 9. This leaves us with a quotient of 2.9, or 2 9/10.
Don't forget, you move the decimal point after you multiply. You count the number of digits to the right of the decimals you're multiplying, then put the decimal that number of places to the left in your final result. You adjust the decimal point before you begin the problem in division. For division, you move the decimal in the divisor to the right of the unit's place. Then, you move the decimal in the dividend the same number of places.
Section D, rounding off with decimals.
Rounding for decimals is similar to rounding for integers, except you can round off numbers to the right of the decimal as well. The steps for rounding off positive decimals are the same as the steps for rounding positive integers. You find the digit place you want to round off to, then oh, look, it's a ladybug. Your second step is to look at the number to the right of that digit place. If it is equal to or greater than 5, then round up the digit you're rounding off to. If it's less than 5, you don't do anything. Here's another example.
Look at the number 3.814, or 3 814
We can round this number to the nearest units place to get the integer 4. That's because the number to the right of the units place is 8, which is greater than 5. So we round the units place digit up 1 from 3 to 4. Our answer is 4, and there's no need to insert a decimal point in this type of answer. You can see that the process of rounding off doesn't change even though the number has a decimal.
So rounding 3.814 to the nearest tenth is 3.8, or 3 8/10. And rounding to the nearest hundredth gives us 3.81, or 3 81/100. In both cases, the digit to the right of the one being rounded off is less than 5, so the digit being rounded off cannot be raised 1.
Notice that we didn't put zeros to the right of the last digit. The value of the rounded number doesn't change either way.
Section E, scientific notation with decimals.
Decimals are often used in scientific notation. Remember, in scientific notation, we're dealing with powers of 10. All we're really doing in scientific notation is moving the decimal point enough places so that the number we're multiplying a power of 10 by is between 1 and 10. And the number of places we move our decimal point tells us what power of 10 we multiply by.
We can use scientific notation to show the distance from the Earth to the Sun, 144 billion meters. We move the decimal place to the left so that the number remaining is greater than or equal to 1 and less than 10. For our number, we move the decimal point over to the left until it's between the 1 and the 4. Our decimal point is now 11 places to the left of where it was. So the answer would be 1.44 times 10 to the 11th power. Notice that 10 to the 11th power is 100 billion. And 1.44 times 100 billion is 144 billion meters.
So up to this point, we've been moving the decimal point to the left, and the power of 10 was the number of decimal places we moved. For numbers less than 1, we have to move the decimal to the right in order to make the number in the units place between 1 and 10. The power of 10 is still represented by the number of places we move the decimal, except the power of 10 is made negative. For example, we'll put 0.0003789 into scientific notation. We must move the decimal 4 places to the right to make the number in the units place between 1 and 10. After moving the decimal point, our number is 3.789. Our power of 10 is -4, since we moved the decimal to the right 4 places. The answer is 3.789, or 3 789 thousandths, times 10 to the -4 power.
Don't forget, to use scientific notation for large numbers, your exponent will always be positive. To use scientific notation for numbers less than 1, your exponent will always be negative.
We've now looked at the different aspects of both decimals and integers. Now let's get to know them a little better.
7 is a young and spicy integer that enjoys music, dancing, and southern cooking. 7 also likes long walks on the beach and the smell of oranges. 7 is looking for a friendship, but is also open to commitment. If you think 7 has your number, dial mailbox 3B7.
2 3/10, on the other hand, is tired of the bitter disappointment of modern dating. 2 3/10 is looking for someone experienced and confident. This person should like movies and laughing and be willing to support 2 3/10 whenever things get difficult. If you want to hook up with 2 3/10, dial mailbox 2A now.
Now on to fractions.
Part 3, Fractions.
We've talked about integers and decimals. When you have a decimal number, all the digits to the right of the decimal represent a part of a whole number. This part of a whole number can also be shown using fractions.
Boy, do I know about fractions. I fell off a jungle gym when I was 5, and I fractioned my arm, like right here, and then...
Section A, fraction terms. A fraction is made up of 2 parts.
The top number of a fraction is the numerator, and the bottom number is called the denominator. In the fraction 3/7, or 3/7, the 3 is the numerator, and the 7 is the denominator.
The numerator represents the part present, while the denominator represents the whole.
So, the numerator is what you still got, and the denominator is what you originally had before I took it from you.
Sort of. Think of a pizza.
Oh, yeah, pizza. No cheese, though.
What kind of a bonehead doesn't like cheese on his pizza?
I just don't like cheese, Klaus.
Okay, you've got a pizza with all 6 slices there, so the part and the whole are the same. That means the value of the fraction is 1, because the numerator and the denominator are the same. You can divide the numerator, 6, by the denominator, 6, to get 1.
Fractions can have larger numerators than denominators, too. If you've got 9 slices, then you've got more than 1 whole pizza. When this happens, the value of the fraction is greater than 1 because the part present is greater than the whole. You've got more slices than there are in a whole pizza. And there's cheese on this one.
Listen closely to this one. Closer. Closer. Sometimes fractions can have different numbers but identical values.
Take, for example, my neighbor 3/8 and me. I mean, we're totally different.
That's right. We don't even have the same denominators, but we both believe in the sacred bond of marriage and family. Yeah. Yeah, tools. Look at you over there with your happy little wife and your happy little house and all your... I have a tank of sea monkeys and a gallon of gas!
Look at the fractions 2/6, 3/9, and 4/12. They're actually all equal to one another. Fractions are kind of wacky, but this will make sense. If we look at these fractions using a pie chart, then they would all represent the same fraction of the pie. Each of these fractions can be reduced to the fraction 1/3.
How do you know you can reduce a fraction? Well, you can reduce a fraction when the numerator and denominator have common factors, like the 3 fractions we just mentioned. So what's a factor, you ask?
A factor is a vital term to have tucked away in your memory bank. A factor of a number is any number that can be multiplied by another number to get the original number.
I like it! Sounds confusing!
Actually, it's not hard at all.
Think of the number 6. Since 2 times 3 equals 6, the 2 and 3 are factors of 6. Likewise, 1 times 6 is 6, so 1 and 6 are also factors of 6. Thus, the factors of 6 are 1, 2, 3, and 6.
So to find the factors of a particular number, you just want to find 2 numbers you can multiply together to get that number. Now, let's return to our fractions and try to reduce them.
We'll start by reducing 2 6. Notice that both the numerator and denominator of this fraction have a common factor, 2. If we divide 2 into the numerator, 2, we get 1. Then we divide 2 into the denominator, 6, to get 3. So the fraction is 1/3.
The value of the fraction hasn't changed. It's just been reduced. The value remains the same because both the numerator and denominator have been reduced by the same number, 2.
The same is true for 3/9 and 4/12. If we divide the numerator and denominator of the first fraction by 3, then the fraction is 1/3. And if we divide the numerator and denominator of the second fraction by 4, then we get 1/3. So 2 6, 3/9, and 4/12 are all equal. Pretty freaky, these fractions, eh? Remember, you reduce a fraction by finding a common factor between the numerator and the denominator. Then you just divide the top and the bottom of the fraction by their common factor.
Now that we've talked about the basics of fractions, let's put these puppies together and take them apart.
Section B, adding and subtracting fractions.
So, now we're going to add and subtract some fractions. But before we do, we got to check the denominators. We got to take one important step if the denominators or the bottom numbers of the fractions are different. We'll look at fractions with common denominators first.
Okay, so let's say 1 pot of coffee has 6 equal cups of coffee in it. Okay, now I'll drink 2. What fraction of my original 6 cups of coffee is left now? I don't know. Somebody tell me, please.
Before we can figure out what fraction is left, we must first figure out how much he drank. He started with 6 cups of coffee, and those 6 cups made up the whole, or 1 pot of coffee. So the fraction for that is 6/6, or 6 cups of coffee out of 6. The amount of cups present were the same as the whole.
Each cup equals 1 cup of the whole, or represents 1/6 of the total amount of coffee he began with. So if he drank 2 cups, then we combine them by adding 1/6 and 1/6. Notice that both denominators are 6. That makes things easy.
When we have the same denominators like we do here, we just add the numerators together. We'll get to problems with different denominators in a second, so you'll just have to hold your horses.
To add these fractions with common denominators, just add the numerators and leave the denominator alone. He can be a little bit grumpy at times. 1/6 plus 1/6 equals 2/6. 2/6 have been drunk. Or, if we reduce this fraction by dividing each part of the fraction by 2, 1/3 of the pot of coffee is gone.
Well, how much is left then?
To figure out how much is left, we need to subtract what has been taken from what was originally there. So we subtract what was taken, 2/6, or 2 cups of coffee, from the whole 6/6, which represents the original 6 cups of coffee.
Just like the addition of fractions with common denominators, we subtract fractions with common denominators by subtracting the numerators while leaving the denominator. So we subtract the numerators. 6 minus 2 equals 4. We leave the denominator, so our answer is 4/6. We could reduce this fraction further by dividing the 4 and 6 by their common factor, 2. Dividing each number by 2 leaves us with a numerator of 2 and a denominator of 3. So after 2 cups have been drank, 2/3 of the original 6 cups of coffee still remain.
Now, if the denominators in fractions being added or subtracted are different, then we've got to alter them so that they have common denominators. Before we get to that, we've got some more terms for you.
We've already looked a little bit at factors. Looking at the factors of a number will determine if the number is prime or composite. A prime number is any number whose only factors are 1 and itself, such as 7. We can multiply 1 times 7 to get 7, but that's it. There's lots of prime numbers. 7, as well as 5, 3, 11, and 23, and 29, and 31.
There's also what? 37, 43, and oh yeah, 17 and 19, 53.
The second type of number is a composite number. This is any number that has more factors than just 1 and itself. 6 is a composite number. 6 and 1 are factors of 6. 2 and 3 are also factors of 6, since we can multiply 3 times 2 to get 6.
Don't forget, a prime number's only factors are 1 and itself. A composite number does have factors other than 1 and itself.
Now that you got factors underneath your belt, we'll look at fractions that don't have common denominators.
In order to add or subtract fractions without common denominators, we must find the lowest common denominator for both fractions. We want to make our denominators as low as possible. If the denominators in your problem are prime, then the lowest common denominator is simply the first denominator times the second.
Why is this? It's because both numbers are as low as they can get. And what you're looking for is the lowest number that both these numbers are factors of. So the lowest common denominator of 3 and 5, both prime numbers, is 15. 3 and 5 are both factors of 15.
All right, we've got one more thing to throw at you.
The lowest common denominator is also 1 times the other, when all the denominators are composite and do not have any common factors other than 1, like 8 and 9.
Both 8 and 9 are composite numbers. 8 has factors of 1, 2, 4, and 8. 1 times 8 is 8, and 2 times 4 is 8. So each of these numbers can be multiplied by another to get 8. 9 has factors of 1, 3, and 9. But 8 and 9 don't have any common factors besides 1.
So since 8 and 9 are composite and do not have any common factors other than 1, we find the lowest common denominator by multiplying them together. The lowest common denominator then is 72, or 8 times 9.
Coming soon, the denominator. He's been sent from the future to save the past. He's part man, part machine, all fractions whiz.
What do you want? The denominator is 72.
That's right. How did you know that?
I am the denominator. I was sent here from the future to help you with your fractions.
Thank you. Thank you.
Scratch my back.
The denominator. Coming soon.
Sometimes you have denominators that are both composite and have common factors other than 1. Remember, a composite number has factors besides 1 in itself. When this is the case, the lowest common denominator is found by finding the smallest number that both denominators have as factors. Let's say you want to find the common denominator for 4 and 10. We'll start with the larger of the two numbers, in this case, 10.
I'm bigger.
Yup.
First, we find multiples of 10. That simply means we're multiplying another number by 10. We're looking for the lowest common denominator possible, so we'll multiply 10 by small numbers first. We start by multiplying 10 times 1. Then we multiply 10 times 2, 10 times 3, and so on, until we find a number that has both 10 and 4 as factors of it.
The first multiple of 10 is 10 times 1, which equals 10. But 4 is not a factor of 10. There's no way to multiply 4 times another whole number to get 10. So we go to the next multiple. 10 times 2 is 20, And from our multiplication tables, we know that 4 is a factor of 20, because 4 times 5 equals 20. So both 4 and 10 are factors of 20.
Remember, you're always looking for the lowest number that each denominator is a factor of. 20 can be divided by both 4 and 10. 20 divided by 4 is 5, and 20 divided by 10 equals 2. 20 is the lowest common denominator for 4 and 10.
Happy hour?
Yeah!
Look at these multiples of 10. Notice that if we continue to find multiples of 10, that 40 is also divisible by 4 and 10. But 20 is lower, and you want to keep things as simple as possible in math.
Sure, if you like to do things the easy way.
We're trying to make the denominators in our fractions the same, but we can't just switch the numbers and go on. We have to multiply the numerator and denominator of each fraction times a number that will make both fractions have the same denominator. Now let's put all this stuff to use and add a couple of fractions.
We'll add these two fractions, 7/12 and 5/18. The first step is to find the lowest common denominator.
We can't add fractions unless the denominators are the same. Both 12 and 18 are composite numbers, so we can look for the lowest common denominator by finding the smallest number that has both 12 and 18 as its factors.
We again start with the larger number, 18. We'll find multiples of 18. 1 times 18 is 18. 12 isn't a factor of 18. We can't multiply 12 by any whole number to get 18, so we keep going. 18 times 2 equals 36. 12 is a factor of 36 because 12 times 3 equals 36.
So, the smallest number that has both 12 and 18 as factors of it is 36. 12 times 3 equals 36, and 18 times 2 equals 36.
Now that we know the common denominator is 36, we can multiply both parts of each of the fractions to make their denominators the same. Remember,
As long as we multiply the numerator and denominator of a fraction by the same number, the value of the fraction doesn't change.
yes. That enables us to make the denominators of both fractions the same without altering the value of the fractions.
Pretty nifty.
I'm impressed.
It doesn't change.
Let's start with 7/12. 3 times 12 equals 36. We also have to multiply the numerator, 7, by 3. That way, the value of the fraction doesn't change. 7 times 3 is 21. So our first fraction is now 21 over 36. Now the other fraction. The denominator is 18. We multiply 18 by 2 to get 36. We multiply the numerator by 2 also to equal 10 for our numerator. So our fraction is now 10 over 36.
Now both of our denominators are the same. We haven't changed the value of either fraction, just altered them so the denominators are the same.
Let's say I like to eat pie, but I can't eat a whole one. So I eat a half, a fourth, or an eighth. And those are all fractions. Those are all fractions. Those are all fractions. Those are all fractions. Those are all fractions.
Okay, we've got common denominators for our fractions. So now that our denominators are the same, we can add or subtract the fractions and then simplify if possible.
We add 21/36 and 10/36. When adding or subtracting fractions, we add or subtract the numerators and always leave the denominator the same. 10 and 21 equal 31. So our answer is 31/36. 31 and 36 have no common factors, so we can't reduce it any further. Our answer is in its simplest form.
We won't do it now, but subtracting fractions is done in the same way as adding.
Remember, when you want to find the lowest common denominator of fractions with different denominators, there are 3 possible scenarios. First, if both denominators are the prime, then just multiply them together. The second possibility is if your denominators are composite, but they have no common factors other than 1. In this instance, you also multiply the denominators together. The third possibility is if the denominators are both composite and have factors other than 1. When this happens, you find the lowest number possible that both denominators are factors of. Then multiply both parts of each fraction so that your denominators are the same. Section C, multiplying and dividing fractions. Multiplying fractions is easier than adding or subtracting them because you don't need to worry about having a common denominator. To multiply fractions, you multiply the numerators together, resulting in your product's numerator, and then you multiply your denominators together, resulting in your product's denominator.
I don't like it. It's too easy.
So let's say you want to multiply 4/3 times 5/8. You multiply the numerators, 4 times 5, to get 20 for your product's numerator. Then you multiply the denominators, 3 times 8, to equal 24 for your answer's denominator. So your answer is 20 over 24.
This fraction can be reduced.
Both numbers in the fraction are divisible by 4. 20 divided by 4 equals 5, and 24 divided by 4 is 6. So our simplified product then is 5/6.
That's it for multiplying fractions. Remember, multiplication saves time and effort.
Mathos. Every year, Mathos engineers work to make life easier for families in America. For years, people have had to add again and again, but through the wonderful new development of multiplication, the average citizen can find totals much easier than ever before. By helping to save time and effort, Mathos is bringing America closer to defeating the communist threat. A Mathos product can be found in every American home.
Now, we'll look at dividing fractions. Remember, we said that division is the reverse of multiplication.
For example, we want to divide 8/3 by 4/6.
Instead of trying to figure out how many times 4/6 goes into 8/3, we use the fact that division is the inverse of multiplication in order to find the answer.
So instead of dividing by 4/6, we flip it to make it 6/4. 6/4 is known as the reciprocal of 4/6.
The reciprocal of a fraction is simply the fraction flipped over. The reciprocal of 8/10 is 10/8.
Hey, so if I stand on my head, does that mean I'm the reciprocal of myself?
Very funny.
Now let's go back to our example.
We flipped the fraction 4/6 to make it 6/4. After flipping one fraction, we just multiply the two fractions like we did before. We multiply 8/3 times 6/4 in the same way we did earlier. We multiply the numerators, 8 and 6, to get 48, and the denominators, 3 and 4, to get 12. Our fraction is 48 over 12.
We need to take one more step in this problem.
48/12 can be reduced because both numbers are divisible by 12. So we divide 48 by 12 to get 4, and then divide 12 into 12 to get 1. Our answer is 4 over 1, or just 4. Why just 4? Because 4 divided by 1 is 4. So the answer to 8/3 divided by 4/6 is 4.
Remember, to multiply fractions, you multiply the numerators together, then the denominators together. Then you reduce the fraction if possible. To divide fractions, you first have to flip one fraction over to find the reciprocal. Then you just multiply the fractions and simplify your answer.
Section D, mixed numbers.
The final type of number that we'll discuss in this section on fractions is a mixed number.
A mixed number is any number that contains an integer and a fraction, like 3 and 1/6. Anytime you're working with mixed numbers, you first want to convert the mixed number to an improper fraction.
What's an improper fraction? Well, an improper fraction is one which has a larger numerator than denominator, so it's kind of top-heavy.
Next, we'll add a couple of mixed numbers, 3 and 1/6 and 2 and 1/3.
Our first step in this problem is to rewrite 3 and 1/6 and 2 and 1/3 to make them improper fractions.
We make them improper fractions because everyone loves a rebel who flouts the conventions of society.
Actually, it's because you need common denominators in order to add fractions, and you can't do that with mixed numbers. There are two ways to convert mixed numbers to improper fractions. Here's the first way.
You want to convert the 3 into an improper fraction that has the same denominator as the fraction. The 6 is the denominator, so we want to make our whole number 3, a fraction that has 6 as the denominator.
How do you do this? The best way is to multiply your whole number times the denominator in your fraction.
So you multiply 3, the whole number, times 6, the denominator. 6 times 3 equals 18. 18 is your numerator. 6 remains the denominator. You haven't changed the value of your fraction. 3 is the same thing as 18/6 because 6 can be divided into 18 3 times. Now you just add 18/6, your whole number, to 1/6, your fraction, to equal 19/6. 19/6 is the same value as 3 and 1/6. You got an improper fraction.
Now we'll do the other mixed number. Another way.
You multiply the whole number in your fraction times the denominator, then add the numerator. So for this mixed number, you multiply the whole number, 2, times the denominator, 3, which equals 6. Then you just add the numerator, 1, to equal 7. This is the numerator in your improper fraction. The denominator stays the same. So 2 and 1/3 equals 7/3.
Either way you convert the whole number, you're going to get the same improper fraction.
We now add 19/6 plus 7/3. We add the fractions just like we have in the past. We first find the lowest common denominator of 6 and 3. The factors of 6 are 1 times 6 and 2 times 3. Since 3 is the other denominator, and it's a factor of 6, we know that 6 is the denominator. So 19/6 stays the way it is, since it already has 6 as a denominator. To make 7/3 have a denominator of 6, we must multiply both the numerator and denominator by 2. That gives us a new fraction of 14/6.
Okay, everybody square dance. Now that the denominators are the same, we can add the two fractions.
Leaving the denominators the same, we can add the numerators 14 and 19, so the sum is 33/6. We're almost done. We can reduce this fraction because both numbers are divisible by 3. So we divide each number by 3 to get 11/2, or 11/2.
We can either leave the fraction this way, or convert it back to a mixed number.
We convert it back to a mixed number by dividing the denominator into the numerator. So 11 divided by 2 is 5 with a remainder of 1. The remainder is the numerator of the new fraction with 5 as the whole number. The denominator stays the same. So 3 and 1/6 plus 2 1/3 equals 5 and 1/2.
That's it for fractions.
If you didn't catch it all the first time, go back and watch it again.
Part 4. Ratios and percents.
For the rest of the video, we're going to take all this stuff we've been learning and use it in some applications.
We're going to apply for a job.
Yeah, we are. So I got an idea. Why don't you go and get your resume?
Section A, ratios. A ratio is a relationship between quantities.
This relationship can be expressed in a number of ways. Like fractions, ratios tell you how much you got in comparison to the whole.
Okay, I'm back for another example. We're going to do a ratio. There's 11 cups of coffee here. 5 are regular strength coffee, 4 are espressos, and 2 are cappuccinos. And they're all for me.
We'll put these into a ratio. You put numbers into a ratio by placing the colons between the amounts present, like the coffee, espresso, or cappuccino.
There are a total of 11 cups, so the ratio is 5 parts regular coffee, 4 parts espresso, and 2 parts cappuccino. We just stick in colons between each of these parts. This means that the ratio of regular coffee to espresso to cappuccino is 5 to 4 to 2.
Notice that there are a total of 11 cups. The 11 represents the whole in this case.
If we looked at this ratio in terms of fractions, then 11 would be the denominator, since it represents the whole, and the numerator would be either the 5 coffees or 4 espressos or 2 cappuccinos. So, the regular coffee represents 5/11ths of the total cups. 4/11 of the total is represented by the espresso, and 2/11 of the whole is cappuccino.
We'll do one more example of ratios.
Was completely and utterly decimated by the power of the volcano.
In a recent poll, 27 students liked the idea of having 2 jiu-jitsu masters engage in combat while their professor lectured,
while 28 students preferred the less violent game of handball.
So, there are 55 students in all, because 27 students plus 28 students equals 55 students.
So, out of a class of 55 students, we have that 27 prefer jiu-jitsu masters as classroom entertainment. The fraction is 27 over 55, or 27 55ths. The numerator, 27, is the part of the whole, or the amount of students out of all those sampled that like jiu-jitsu. And 28 out of 55 students are for handball. And this fraction is 28 over 55, or 28 55ths. So 28 out of 55 students preferred handball. It's that easy.
Section B, percent.
Percentages are the final application we will discuss.
You've probably been exposed to percentages before.
Percentages.
Percent comes from the Latin meaning per hundred. Basically, it's just a number over 100. So 50% is equal to 50 over 100. This can also be reduced to 1/2 as a fraction or 5/10 as a decimal. They all represent the same amount.
To convert a decimal such as 35 hundredths or 0.35 to a percent, simply move the decimal point 2 places to the right and insert the percent symbol to obtain 35%. Why? Because essentially all you're doing is multiplying 0.35 times 100. Remember, each zero represents a digit place. 100 has 2 zeros, so the decimal in the number you're multiplying 100 by must move 2 digit places to the right. Look at the number 1.695. To make this number a percent, we again move the decimal place 2 digits to the right, or multiply it by 100. So, the decimal 1.695 becomes 169 5/10%. Simple as pie. And when you're doing percent problems, write the sign like this, to brighten someone's day.
To convert a fraction to a percent, you divide the denominator into the numerator. Once you have a decimal, then you move the decimal 2 places to the right and insert the percent symbol. Or you can multiply by 100%. That is, if you're into that sort of thing.
Let's go back to our classroom example. Remember, a poll was taken recently showing that 27 people out of 55 prefer jiu-jitsu masters in their classroom. We want to find out what percentage that is.
The first step is to convert the fraction 27 over 55 into a decimal. We know that we can convert the fraction 27 55ths to a decimal by dividing 55 into 27. Notice that the denominator is the divisor and the numerator is the dividend. After dividing, we get the decimal 0.49090909.
090909. Oh, sorry. Okay, now let's find the percent of this decimal.
To obtain the percent, move the decimal point 2 places to the right and insert the percent symbol. So we have 49.0909%. We can round this off to 49%. So 49% of the students prefer jiu-jitsu masters over handball.
This ends our study of percents and the basics of numbers and mathematical operations.
The end of basic math.
Well, we've covered lots of mathematical subjects, like the division, multiplication, addition, and subtraction of integers, decimals, fractions, and mixed numbers.
And we've cleared up that order of operations stuff. Be sure to look for other math tapes like Algebra 1 and 2, Pre-Calculus 1 and 2, and Trigonometry.
Even though I'm not in most of those tapes.
And if you have any questions or you just get confused, give us a call here at Cerebellum at 1-800-VCR-REVIEW. We'd love to hear from you. Bye-bye.
Bye.